Good morning everyone. Today we will be discussing about the stress transformations on Mohr circle. Before that, let me say how many marks strength of materials will be having or the weightage of the strength of materials in IES and GATE. So if you see the weightage of strength of materials in IES and GATE, this will be in the range of 30 to 40 marks, and this is for 5 marks. Normally the maximum marks would be for 5 marks, and since for 2017 the conventional paper is having 300 marks, there is every possibility of plus 10 marks in this range. Now we will be discussing about the stress transformations and Mohr circle. What exactly is these things? If you consider an element of the stress, so if you consider this as an element, the stresses on this element would be sigma x in this direction, sigma y in this direction, tau xy in this direction, and tau yx in this direction. The same mirror image would be seen in the opposite direction. This is sigma x, this would be sigma y. So this will be the stress element. What is stress transformations? Like if you got an element like this, and we have to calculate the stresses in any other plane. Let us say if the plane is making an angle theta, this is one of the plane, and we have to calculate the normal stress on this plane, shear stress on this plane. So normal stress and shear stress on this plane is to be calculated. This can be done by two methods. First one is analytical method. Second one is Mohr circle method. Mohr circle method, or it could be also called as geometrical method. So today I'll be showing you the way to calculate these stresses by using both the methods, analytical method and Mohr circle method. First, analytical method. This is analytical method. And if you consider a triangle like this, like it's a part of stress element that I have shown earlier. So this is sigma x, this is sigma y, this is tau xy, this could be tau yx, this is theta, this is just part of the previous element I am showing here, and I am naming this as A, this as B, this as C. And if you see from this diagram, today we will be calculating sigma n and tau xy dash. So how we will be calculating that? See, normally to calculate the stresses, we will be taking the force equilibrium equation in any direction. Here we will be taking the force equilibrium equation in both, let us say, in NN direction will be the direction of normal stresses, TT direction will be the direction of the tau xy. So if you take this as the axis, x, y, and this as n direction on which sigma n is acting. So for example, let us say if we consider unit length, unit thickness of the element, this would be sigma n multiplied with AC. And on this direction it would be sigma x multiplied with AB, and AB multiplied with 1 actually, because as I am considering this as unit thickness, I will be taking this as sigma x multiplied with AB, and this is theta, this is tau yx, because tau xy is acting in this direction, so tau yx multiplied with BC. The area would be BC multiplied with 1, and along this direction it would be sigma y multiplied with BC, and this would be tau xy multiplied with AB. So if you equate the forces in the n direction, like F n is equal to 0, then you will get sigma n multiplied with AC equal to sigma x AB cos theta plus tau yx BC cos theta plus sigma y BC sin theta plus tau xy AB sin theta. And from this triangle what we can get is sin theta is equal to BC by AC, and cos theta is equal to AB by AC. AB by AC. So if you substitute those values in this one, the final equation of sigma x would be, sigma n. Sigma n would be sigma x cos square theta plus sigma y sin square theta plus tau xy sin 2 theta. So this is the final equation of the stress or normal stress on any plane which makes an angle theta with the vertical. This is how we will be calculating the normal stress. Now we'll see how we will calculate the shear stresses in this direction. It will be like the same method where you will be taking FTT is equal to 0, and the final equation you will get is, what you get is let us say this is the, so this would be the TT tau xy AC. So I am calling this as TT direction. I am taking FTT is equal to 0, as before that I have shown the sigma x multiplied with AB. This would be tau yx multiplied with BC, and this is sigma y multiplied with BC, and this one is tau xy multiplied with AB, and this is here, this is 90 minus theta, not theta. This will be 90 minus theta. So if you take FTT is equal to 0, the final equation for tau xy dash you will be getting would be equal to sigma y minus sigma x by 2 sin 2 theta plus tau xy cos 2 theta. Now here, based upon the taking the moment about any point, this is the normal thing which you will be seeing in the stresses actually, that tau xy will be equal to tau yx. This you will be getting by taking the moment about this point. This will be appearing only if theta between these two planes will be perpendicular, that is 90 degrees. And this is the basic thing, assuming that you know this. So the tau xy dash is equal to sigma y minus sigma x by 2 sin 2 theta plus tau xy cos 2 theta. These are the final two formulas that is used to calculate the stresses, normal stress and shear stress on any plane. Now if you see, why I have to calculate these things? These things are to be calculated from design purpose. If you see, this is the normal stress. I have to calculate, if you calculate maximum normal stress, let us say, that is, if you want to calculate maximum normal stress, tau sigma n by tau theta has to be made equal to 0. Why? What is the use of getting maximum normal stress? From maximum normal stress, let us say I got a stress of sigma p. This is the maximum stress. While designing for any element, we will design for the maximum stress. Let us say the strength of the element or yield strength of the element is sigma y. the factor of safety would be given as, this is one of the theory, not this theory is called maximum principal stress theory. From that theory you will get factor of safety is equal to sigma y by sigma p. If you take any theory like maximum principal stress theory, maximum principal strain theory, strain energy theory, shear strain energy theory, sigma p max or the maximum principal stresses and maximum shear stresses are required for designing the element. That is the major idea of calculating sigma n and tau xy. If you take sigma n by sigma theta is equal to 0, that is, if you differentiate it, finally you will get an answer like tan 2 theta p would be is equal to tau xy by sigma x minus sigma y. So this is the plane on which you will get the maximum principal stress. And these planes for biaxial stress problem, there will be two mutual perpendicular planes like this, which I will be showing in the next diagram. And if you substitute this tan 2 theta p in the tau xy dash equation, like if this is tan 2 theta p, sin 2 theta p is equal to tau xy by under root of sigma x minus sigma y whole square plus tau xy whole square cos 2 theta p is equal to sigma x minus sigma y by under root of sigma x minus sigma y whole square plus tau xy square. If you substitute these two values over here, sin 2 theta and cos 2 theta, you will get tau xy dash equal to 0. That is, shear stresses on this plane is equal to 0. Hence, this stress and the stress on the plane sigma n, after substituting tan 2 theta is equal to this value, you will get tau xy dash is equal to 0, and sigma n would be equal to sigma n, this can call as sigma p. Sigma p is equal to sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 whole square plus tau xy square. So this is the maximum principal stress, and this is the plane. On this plane shear stress would be equal to 0. Hence it is called as the plane on which shear stress equal to 0 is called principal planes, and the normal stresses on these planes are referred as principal stresses. For biaxial stress problem, if you see, for biaxial stress problem, this is sigma x, this is sigma y. Let us say at an angle I got the maximum principal stress plane. This is theta p. On this plane, shear stress is normal stress is maximum. Normal stress is maximum, shear stress equal to 0 on this plane. So this would be like this. This is sigma p. And for biaxial stress problem, two such planes exist. Like for theta p it is 0, theta p, sigma p is maximum, that tau max would be equal to 0. And for, if I say this, if I take this as theta p1, for theta p2 that is equal to theta p1 plus 90 degrees, tan 2 theta p2 would be equal to tan of 2 theta p1 plus 90 degrees. Tan 180 plus 2 theta, that is tan 180 plus 2 theta would be equal to tan 2 theta. Tan 2 theta p1. So two such planes exist which are perpendicular to each other. This is sigma p1, this is sigma p1, this would be sigma p2, this would be sigma p2, on which shear stresses is equal to 0. Maximum of these two stresses will be absolute maximum, and minimum of these two stresses will be the absolute minimum. For triaxial plane, you will get three such stresses, and maximum of all these three stresses will be considered as absolute maximum, and minimum will be considered as absolute minimum. So this is how the location diagram will be shown. That is, if at all in examination, if they ask you to show the sigma p1 and sigma p2, this is how you have to show. Because on this plane, this is sigma p1 and sigma p1. This is 90 degrees to this one. This will be sigma p2, sigma p2. This is first principal plane, this is called second principal plane. Now we will see maximum shear stress. For maximum shear stress, dou tau x by dou theta should be made equal to 0. And once, tau xy dash, earlier we got that equation. If you make this equal to 0, then you will get tan 2 theta t. Let us say this as tan 2 theta t, that would be equal to sigma y minus sigma x by tau xy. Whereas tan 2 theta p is equal to tau xy by sigma x minus sigma y. So once if you keep these two things, once if you see these two things, multiply these two things, tan 2 theta p, tan 2 theta t, multiplied with tan 2 theta p is equal to minus 1. This shows that these two things are perpendicular to each other. That means 2 theta t is equal to 90 plus 2 theta p. That is theta t is equal to 45 degrees plus theta p. 45 degrees plus theta p, and this on this plane you will get the maximum shear stress. This is the plane. So theta t is equal to 45 degrees plus theta p. That means the maximum, if I consider two planes on which the two principal planes, that is sigma p1 and sigma p2, which are 90 degrees to each other, I have now shown that tau max plane will be at an angle of 45 degrees to this one. So that is tau max plane bisects sigma p1 and sigma p2. This will be asked in the objective questions. So just by looking at it, or in assertion and reason questions, where they will ask you like tau max plane bisects principal planes, or maximum shear stress plane bisects the principal planes, and hence it is right. So if you see that as the answer, it is right, or in assertion and reasoning also we can say that is correct answer. And now tau max can also be, from here the tau max can be written as sigma p1 minus sigma p2 by 2. Same thing for this one. Two such planes exist for tau max plane. Two such planes exist for tau max also, and absolute maximum of two things will be the maximum shear stress. This will be used in maximum shear stress theory for designing a material by using maximum shear stress theory. Like factor of safety at that point of time would be equal to sigma y by 2 by tau max by 2. Tau max, not tau max by 2, tau max. Tau max normally you get as sigma p1 minus sigma p2 by 2. That is factor of safety would be equal to sigma y by sigma p1 minus sigma p2. This is used in maximum shear stress theory. That is normally used for designing the ductile materials. The location diagram of maximum principal stress and maximum shear stress will be like this. If you see on this plane, let us say this is the maximum principal stress plane. This is theta p, maximum principal stress plane, that is sigma p1 and sigma p1, sigma p2 and sigma p2. And I have already shown you like this bisects. So if you take the bisector of 45 degrees for this one, on this plane you can show the maximum shear stress. This is the maximum shear stress. This is the maximum shear stress. So these are the planes. Maximum shear stress. And there will be some amount of normal stress on these planes also. Sigma n1, sigma n1, sigma n2 and sigma n2. So if they ask you the location diagram after calculating all the stresses, this is how you have to show finally for the exam in the examination. Now on the maximum principal stress plane, if you substitute, you get sigma n1 is equal to sigma n2, and there is a concept called stress variant. On that basis, sigma p1 plus sigma p2 by 2 would be equal to sigma x plus sigma y by 2. That is, sum of the stresses, sum of the normal stresses on any plane or two perpendicular planes will be same. Sum of the normal stresses on two perpendicular planes will be same. Now coming to the graphical method. Graphical method is Mohr circle method. In Mohr circle method, that is, take a circle. This is tau axis. This is sigma axis. This is tau axis. This is sigma axis. And why I have to go for the geometrical method? Because as I have seen the variation of theta for small angle, for 30-60 we can easily calculate by analytical methods. For very small angles, calculating each and everything will be difficult. So if you draw the Mohr circle, just by looking at the point or just by locating the point, you will get the stresses on that plane, that is normal stress and shear stress on that plane. So this would be the Mohr circle. So let us consider this as the Mohr circle. So the circle touches the sigma at 2 points, and tau would be equal to 0 on these 2 points. So this would be sigma max or sigma p1, maximum principal stress, 2, and this is the tau max. On any point on this circle represents a plane, and the coordinates of this plane would be sigma and tau. That is, normal stress and shear stress on that plane can be calculated just by locating that point. So sigma p1, sigma p2. This is tau max plane. This is the tau max plane. So this is the center. How will you get the center? Center would be equal to sigma p1 plus sigma p2 by 2 comma 0, and the radius would be equal to tau max, or radius can also be written as sigma p1 minus sigma p2 by 2, that is equal to tau max. So this is the radius of the Mohr circle, this is the center of the Mohr circle. And why I have to keep the center on sigma axis only? Why can't above or below? This question will be asked in interviews. Like if you see, if I keep the center of the Mohr circle above, let us say if I keep the center of the Mohr circle above, this represents the plane on which tau max equal to 0. So on these planes, whatever the normal stress that we are calculating, it should be the maximum. But according to the circle theory, the stress, these values would be maximum. That if I say this is sigma p1, this is sigma p2, this is sigma r1, sigma r2. So these are the max. Sigma p1 is greater than sigma r1. So you can't say, but according to the theory that I have explained before, that on tau max, on the planes on which tau is equal to 0, those are the planes we will be getting the maximum principal stress and maximum principal stress planes. So that theory is violated over here. Hence, the center has to move onto the x-axis. So center will be at the x-axis. So that sigma p1 and sigma p2, sigma p1 and sigma p2 will be the principal stresses. This would be the maximum, this would be the minimum. And now for a given stress element, how we are going to locate or how we are going to draw the Mohr circle. Let us say they have given me sigma x, sigma y, tau xy, tau yx. So if you know these 2 points, that is the sigma x and tau xy and sigma y and tau yx, the sign conventions are very much important over here. If let me say this is tau axis, this is sigma axis. If sigma is positive, I mean this is the positive. If it is in tension, for tension it is taken as positive, so it will be right side of the tau axis. The point will be represented on the right side of the tau axis for tension. For compression, the point will be represented on the left side of the tau axis. Left side of the tau axis for compression. And if it is clockwise moment, then it would be above sigma axis, clockwise. Above sigma axis. And if it is anti-clockwise moment or anti-clockwise tau xy, it is not moment over here, it is stresses. If these shear stresses produces a clockwise moment, then it will be considered as it will be taken above sigma axis, and this is anti-clockwise moment. For the anti-clockwise moment, it will, for anti-clockwise direction, it will be taken below the sigma axis. So these are the sign conventions. You have to remember these sign conventions while solving the problems. So once if you get these values, sigma x and tau xy, sigma y and tau yx, plot those values first of all. So plot those 2 points. Once if you plot those 2 points and join that by a line, so this will be the center of the circle. This will be the center of it. That is, the line where it cuts the sigma axis will be the center of the circle. With O as center and OA or OB as radius, draw a circle. Draw a circle. This is the required Mohr circle. From this, you will get this as sigma P1 and sigma P2. If you want to calculate on any angle theta, let us see. If you want to calculate stresses on any angle theta, so first let me say this is A, this is B, this is C, this is D. So then I name this one as R1, R2. So first of all, we have to locate this point. This point is called pole. This can be located by drawing the horizontal line from here and vertical line from here. If you draw the vertical and horizontal line, the point where it meets the circle will be the point A. It can be done like this, or it can also be done like this. These both the things represent the same point. And once, if you want to calculate the maximum principal plane theta p, just join these 2 points with a straight line and measure the angle with the protractor. That would be theta p1. And if you want to calculate theta p2, this is how you will calculate this one as theta p2. And remember, anti-clockwise, here it is theta is anti-clockwise, which is taken as positive. If it is clockwise, it will be taken as negative. So this is how theta p1 and theta p2 is calculated. And if at all any angle we have to calculate stresses, so just with respect to this point, at any angle, if you consider theta, draw a line. Let us say if theta is given to you, with respect to this point, take an angle. I think you understood this theta p1 and theta p2, so I am writing this one. This is like this, this will be like this. This is A. This is theta p1. So if at all there is any point, let us say theta, which will be maintained like this, this is theta. So this is the point, let us say B, on which you want to calculate the normal stress and shear stress. Just with respect to this one, by using protractor, mark the point B over here, and this is theta 1, theta 2 would be equal to, let us say, like this. This is theta 2 plus 90 degrees. So based on these two things, you can calculate the normal stress and shear stresses. That is theta 1 plus 90 degrees. Normal stress and shear stress. If you know this point, you can easily calculate the normal stress and shear stress on this point. So that represents the normal stress and shear stress on any plane. So each plane is represented by a point in the mohr circle. So that's how it becomes easy to calculate the normal stress and shear stress on any plane. So if you consider, and another property would be like if two planes are making an angle of theta degrees, in this one, in mohr circle, these two planes will make an angle of 2 theta with respect to the center. With respect to the center, these two planes will make an angle of 2 theta. This is one of the important points which can be asked in the objective questions. And if you take one of the example for like pure shear condition, if you take pure shear condition, which normally you will see in the torsion things, like this is tau, this is tau, this is tau, this is tau. Sigma P1 and sigma P2, if you calculate, we'll get the values as plus or minus tau. So sigma P1 would be tau, which will be at theta P1 is equal to 45 degrees. Theta P2 would be equal to minus tau, which will be at theta P2 is equal to 135 degrees. So once if you want to draw a mohr circle for this, and tau max would be equal to tau. And if you have to draw the mohr circle for this, this is how the mohr circle looks like. This is just one of the example. This is how the mohr circle looks like. This would be sigma, that is tau comma 0. This is minus tau comma 0. This is 0 comma tau. This is also 0 comma minus tau. So if you see here the normal stress is equal to 0. The plane in which normal stress is equal to 0 is called pure shear plane. Pure shear plane. So this is just one of the example for mohr circle. And now with this, I am concluding my session today. And the subjects I want to teach in your academy is strength of materials, geotechnical engineering, fluid mechanics, CPM PERT, irrigation. That's it. Thank you very much.